We recall how the inverse kinematics problem can be solved as a minimization problem, minimizing the distance between our desired goal position of the end effector and the actual position of the end effector. This optimization problem defines an objective function. Assuming an Euclidean distance, we can write out the objective function as follows. We see here that it's basically the inner product of two vectors, being the difference vectors between the goal and the end effector. To increase readability, we will introduce some shorthand notation to make the math more readable. So when we write the g vector, it's implicitly assumed that this will be the homogeneous version of the d vector. When we use the end effector function, uppercase F, we are gonna assume implicitly that the tooltip vector is a constant, which means we're just gonna write it as f of theta. When we look at the partial derivative of the end effector with respect to theta k, that is the kth column of the Jacobian, we're gonna introduce the notation of using an uppercase J for the Jacobian matrix and a sub-index k for the k column. The gradient of the objective function is defined as follows. It's defined as the partial derivative of the objective function with respect to the link angles. We can write this out. So the partial derivative would be the objective function taking the derivative with respect to the first link angle. The second component would be the derivative with respect to the theta 1, and the third would be with theta 2, and so and so. We will now just study a component, the jth component of the gradient. So we write up the definitions here. We take the partial derivative with respect to theta j of the definition of the objective function. We apply the product rule and simplify, so we get to the results shown here. We have a difference between the goal and the end effector, multiplied by the partial derivative with respect to theta j of the difference vector. G is a constant, so the partial derivative of that is 0, so that goes out, minus, we pull outside, and what is left is the partial derivative of the end effector with respect to theta j, but that is just the jth column of the Jacobian matrix. Hence we have found the gradient, or the jth component of the gradient of the objective function. Collecting all components into one full vector, we find the final results. The gradient of the objective function is equal to minus j times the difference vector between the goal and the end effector position. Next, we wish to find the Hessian of the objective function. So the Hessian is the double derivative of the objective function. It's a symmetric matrix. So here we're just going to assume that the ith index is less than j. And we're going to apply the previous results, so we know what the objective function taking the derivative with that respect to theta j is, so we substitute that in. Then we're going to take the derivative of that with respect to theta I. We immediately take the minus outside, so we are left with this expression here. Then we will apply the product rule, taking the derivative of the first term multiplied by the second term plus the first term multiplied by the derivative of the second term. This is written out here. Looking more closely at the first term, we notice that partial derivative applied to the difference vector. G is a constant, it will go away. Minus takes minus becomes a plus. Partial derivative of the end effector becomes the ith column of the Jacobian, which means that the first term simplifies to the ith column of Jacobian multiplied by the jth column of the Jacobian. The last term we have the difference vector between the goal and end effector multiplied by the partial derivative of the jth component of the Jacobian with respect to theta I. This term looks complex. An often assumption that's used is that if one is close by to the goal, the first part, meaning the difference vector, is going to be very small, and people often neglect the second term here. Due to this argument, we will now try to figure out a way to actually solve for this in an exact way. To do so, we're going to recall the previous knowledge we have about how the end effector is written up as a multiplication of transformation matrices and how we computed the Jacobian previously. When we do that and we take the derivative with respect to theta I, we will reach the following result, looking like this. Now we're gonna reapply the idea of looking at this in a geometric way. So we're gonna read this equation from the back to the front. If we look at this part of the equation, we know this is the hat of the difference vector between the end effector and the origin of the jth link. Now, this part will transform that vector into the ith coordinate system and then take the hat of that vector, and the last part is going to transform that vector into a world coordinate system. So this basically means that we are gonna apply 2 times hat to the difference vector between the end effector and the jth origin. 2 times hat is basically minus the original vector. So this boils down to that the partial derivative of the jth column of Jacobian with respect to theta I is actually equal to minus the jth column of the Jacobian. Substituting into the Hessian formula we have derived, we now discover the exact formula for the Hessian. This looks like this. Knowing how to compute the gradient and the Hessian, we are ready to solve this numerically using numerical optimization.